Do you remember what happened in 1993? Well, maybe not. Doom released. Later on, we began pushing the engine to its absolute limits, creating massive custom maps filled with thousands of monsters and items, which led to a very specific and fatal flaw surfacing. When players tried to save their progress in these custom levels, the game would crash straight back to DOS. And this was not a random glitch. This was one of the most famous early examples of buffer overflow. To understand why this happened, we have to look at how vanilla Doom handled memory. The game's engine allocated a strict, fixed amount of space specifically to hold save game data. As long as you played the standard maps, everything fit perfectly, but when custom maps generated too many entities to keep track of, the save data grew far larger than the space the developers had originally set aside for it. That fixed memory space is what we call a buffer. You can think of a buffer like a physical glass of water. It has clear maximum capacity. If you keep pouring water into the glass after it is already full, the water doesn't just disappear, it spills over the rim. In computer memory, when you pour too much data into a buffer, the excess bytes spill out and every byte adjacent memory addresses. In Doom, this spillage overrode critical game instructions, causing the entire program to collapse. In this video, we are going to look at exactly how this catastrophic spillage happens at the bare metal memory level. We will examine the mechanics of the call stack, write our own vulnerable retro-style C++ game code, and use a classic memory overflow exploit to hack our own program and unlock God mode. Finally, we will look at how modern compilers and operating systems have evolved to stop us from pulling off the same tricks today. When you run a C++ program, or any program, the operating system hands it a chunk of RAM to work with. This memory is organized into distinct segments. At the bottom, you have the text segment, which holds the compiled read-only machine code. Above that is a data segment, where global and static variables live. Then comes the heap, a large pool of memory used for dynamic, on-the-fly allocations when you don't know how much space you will need until the program is already running. But the area we are interested in sits at the very top of this memory space. It is fast, highly structured, and it is called stack. The stack manages the timeline of your code, keeping track of which function is running and what local data it needs at any given moment. It operates on a strict last-in, first-out principle, also known as LIFO. Imagine a stack of plates in a cafeteria. When a clean one comes out of the kitchen, it is placed on top of the pile. When someone needs a plate, they take the one from the top. You never pull a plate from the bottom. The computer's call stack works the same way. When your program calls a function, it pushes all the necessary data for the function onto the top of the stack. When the function finishes, the data is popped off and discarded, leaving the previous function back on top. Every time a function is called, it gets its own temporary workspace on the stack. This block is known as the stack frame. When the program starts, the main function gets the first frame. It runs its loop and asks for input. The moment we type in our password and the code calls check password, the CPU pauses main and pushes a new stack frame into the stack for the check password function. This new frame stores the arguments passed to the function, in our case a pointer to the input password. Next, and this is highly relevant to security researchers, the CPU pushes a return address onto the stack. This is a precise location telling the computer where to resume execution once the function finishes. Finally, the frame allocates space for local variables. In our example, that includes the old stack frame structure, containing the 8-byte password buffer and the 4-byte God mode flag. All of these components, the arguments, the return address, and our local variables, are crammed together sequentially inside this temporary stack frame. To navigate this workspace, the processor relies on two specialized registers. The first is the stack pointer, known as ESP in 32-bit systems, or RSP in 64-bit systems. it always points to the top of the stack. Whenever data is pushed or popped, the stack pointer moves accordingly. However, because the stack pointer is constantly moving as the function works, it is a terrible reference point for finding specific variables. That is where the base pointer comes, known as EBP. When a stack frame is created, the base pointer is set at the bottom of that frame and remains fixed during the function call. It acts as a stable anchor. Instead of tracking the shifting top of the stack, the CPU accesses variables using fixed offsets from this base pointer, making it easy to find data reliably. And now, consider how our data is laid out. In our code, we declared an 8-byte character array password buffer, followed immediately by a 4-byte integer God mode flag. You might think older systems from the early 90s just packed variables tightly together with no padding because memory was limited. But that's not true. Even early compilers automatically inserted invisible padding bytes between variables to align them properly and prevent severe CPU performance penalties. So why are our two variables sitting right next to each other in memory without any padding? Because of mathematical coincidence, natural alignment. An 8-byte array perfectly fills up exactly two 4-byte machine words. Because the math lines up flawlessly, the compiler realizes it doesn't need to insert any invisible padding bytes before placing our subsequent 4-byte God mode flag. Let's bring our source code on screen and see this vulnerability in action. Welcome to Star Citizen 92, our custom DOS terminal simulator. If you look closely at the check password function, you will see exactly how we are mimicking the dangerous memory layout. We have placed our 8-byte password buffer and our 4-byte God mode flag inside a single struct called old stack frame. As we discussed, this guarantees that these two variables are forced into adjacent memory addresses, completely bypassing the automatic reorganization and padding that modern compilers use to protect us. The vulnerable function here is string copy. It copies a string from one location to another, character by character, until it reaches a null terminator, a 0-byte marking the end of the string. The problem is that string copy doesn't know the size of the destination buffer. It doesn't check boundaries. It simply keeps copying, assuming the programmer allocated enough space. I believe you are starting to see where this is going. Now, let's run the program normally and enter the intended password, plasma. This word has 6 characters, plus the null terminator makes 7 bytes total. That fits safely within our 8-byte buffer. If you look at the memory dump, you will see the characters neatly stored inside the buffer, and right after that, the God mode flag, which remains untouched, still 0. The program behaves as expected, but what happens if we break the rules? We are going to type something massively oversized, like plasma, plasma, plasma. Remember, our dedicated container can only hold exactly 8 bytes. The moment we hit enter, the trap springs. If you look at the terminal output, the memory devastation is completely visible. The first 8 bytes of our password buffer are entirely saturated with the beginning of our giant text string. But because the string copy function refused to stop copying until it found a null terminator, the excess characters had nowhere to go but forward. They spilled violently over the strict 8-byte boundary and slammed straight into the adjacent memory space. In the hex dump, you can clearly see the hex values for our overflowing letters completely overwriting the zeros of our God mode flag. This act of spillage completely messed up the logic of the entire application. We didn't write a virus, and we did not modify the game's actual executable code as many times before. We simply manipulated the data environment that the code relies on to make decisions. Because the memory address for the God mode flag is no longer reading as 0, the game assumes we legitimately earned the upgrade. Just by typing too many characters into a prompt, we have successfully corrupted the application state and granted ourselves infinite lives. While this example is harmless and even fun, the real danger is far more serious. Beyond local variables lies the return address. If an attacker carefully crafts their input, they can override that return address as well. Instead of returning to the correct place in the program, the CPU jumps to an attacker-controlled location and executes malicious code, often referred to as shellcode. This is the foundational technique behind some of the most devastating cyber attacks in history. Back at our code, we deliberately bundled our variables into the old stack frame structure to simulate the dangerous behavior from the past. Over the past decades, compiler engineers and operating system developers have implemented layers of countermeasures to kill these exact exploits. The first major line of defense is something called the Stack Canary, named after the old coal mining practice of bringing a bird underground to detect toxic gas. A Stack Canary is a random secret value that the modern compiler automatically injects into the stack frame. It sits right between your local buffers and the critical control data, like the return address. When a function finishes its work, before it does anything else, it checks to see if that secret value is still intact. If a rogue string copy function spills over its boundaries, it will inevitably crash the canary. The system instantly detects the corruption and violently aborts the program before the attacker's payload can ever execute. But let's say that incredibly persistent attacker somehow bypasses the canary. They manage to override the return address and successfully point it toward their injected malicious shellcode sitting right here on the stack. This is where the hardware itself steps in with a feature called data execution prevention, often driven by the NX or no execute bit. Modern processors allow operating systems to explicitly label different areas of memory with specific permissions. The text segment is marked as executable because it contains your actual compiled program, but the stack is strictly marked as data only. If the CPU is tricked into jumping to the stack and attempts to run the attacker's raw shellcode, it looks at that non-executable flag and flat out refuses to process the instructions. It essentially enforces the rule that this area of memory is exclusively for storage, not for execution. But hackers rarely just give up. To bypass this, attackers developed a highly complex technique called return-oriented programming, or ROP. Instead of running their own injected code, they carefully override the stack to chain together tiny snippets of legitimate code that already exist elsewhere in the program to do their dirty work. To stop attackers from finding those existing code snippets, we have address space layout randomization, or ASLR. The operating system randomizes the locations of the stack, heap, and code every time a program runs. This makes it difficult for attackers to know where to jump unless they manage to exploit yet another bug to leak a memory address and calculate the layout on the fly. That would be all for today. If you would like to learn more about memory, how it works, how data are stored, click on this video. Thanks for watching. If you like what you saw and want to see more in the future, click the subscribe button, and ciao!